Welcome students to MOOC's series of lectures on non-parametric statistical inference. This is lecture number 6. As I said at the end of last class that in this lecture we shall study some tests for goodness of fit. Now, the question is, what are tests for goodness of fit? Basically, this is about obtaining information about the form of the population from which a sample is drawn, and the focus of the investigation may be the shape of the underlying distribution. Let me now illustrate with respect to one example. Suppose one wishes to check if a coin is unbiased from the outcomes of n tosses of the coin. We know that if the number of tosses is n, then the shape of the distribution will depend upon the value of p, which is the probability of obtaining a head in a single toss of the coin, or in other words we call it the probability of success. If the coin is unbiased, that is p is equal to 0.5, we know that the distribution is symmetric about the mean. For illustration, let us look at the graph that we have plotted. Here n is equal to 10, p is equal to 0.5, and therefore, mean is 5, and we can see that the distribution is symmetrical in the range 0 to 10 for the binomial 10, 0.5 variable. The question is, what happens if the coin is not unbiased? So, if the coin is not unbiased, p is different from 0.5, it may be higher, it may be lower than that. So, let us consider a p which is say 0.75. Then for the same n, that is 10, we get a distribution which will look like this, which is given in the figure A. And as you can understand that since the value of p is equal to 0.75, the probability of getting more heads is higher than getting a lesser number of heads, and consequently, this is the type of distribution that one can obtain with the mode value at 8. On the other hand, if the value of p is significantly lower than 0.5, so for this illustration we have considered it to be 0.25, and we can see that the bar chart describing the probabilities look like this, which is not symmetric around the mean at all, and we can see that it has a skewed distribution. Therefore, suppose we get a discrete distribution from the observed sample, something similar to this, which we can see is skewed on this side. Therefore, it is quite natural that we will like to test whether it is coming from a binomial distribution with p is equal to 0.25 for an appropriate value of n, and that is what testing of hypothesis is all about. Let me give you another example. Suppose we want to test whether a dice is unbiased, that is, each of the 6 faces of the die will have equal probability. Therefore, the hypothesis that we are testing is p 1 is equal to p 2 is equal to say up to p 6, and each one of them is 1 by 6, where p j is probability that x is taking the value j, where x is the random variable indicating the outcome of a single roll of the dice. Question is how to test that. Let us understand that if the coin is unbiased, it does not mean that in 100 tosses we shall get exactly 50 heads and 50 tails. That may not happen, but there will be deviations from this obtained value from the expected value n p. However, if the deviation is too much, then we would say that it is not acceptable, and or in other words we are going to reject the null hypothesis. So, corresponding test we need to do. The major test in this regard is chi-square test, which has several subtle variations, but we shall study the basic chi-square test today. So, the idea of frequency chi-square is like this. Suppose a population consists of mutually exclusive classes with the proportion of members belonging to jth class is p j. What does it mean? It means that suppose this is the entire population, it is divided into several classes. Suppose in this case I have taken 4 classes. So, P 1 is the proportion of elements belonging to class 1, P 2 is the proportion of elements belonging to class 2, like that for class 3 and class 4. And we have to understand that they are mutually exclusive. That means that no element can belong to 2 of these classes at the same time. Now, sigma p j, j is equal to 1 to k is equal to 1, where k is the number of classes. Now, suppose we have taken n samples from the population. The probability that there are n j many objects from the class j, j is equal to 1 to k, can be obtained using the multinomial distribution. I hope you are familiar with multinomial, but I will explain it now. If k is equal to 2, then we get a binomial distribution. So, what is multinomial distribution? With parameters p 1, p 2, p k and n, which is the number of samples, the probability distribution will look like this: n factorial upon n 1 factorial, n 2 factorial into n k factorial into p 1 to the power n 1, p 2 to the power n 2, p k to the power n k, where n 1 into n k is that n 1 is number of elements in the sample from class C 1, similarly n 2 from C 2 and n k from C k. N 1 plus n 2 plus n k is equal to n, the total number of samples. Now, how do we get that? It is very simple. So, out of n, we first select n 1 of them. That can be done in n c n 1, and let us put them in class number 1, that is C 1. So, that probability is p 1 to the power n 1. Now, how many are remaining? N minus n 1 are there. So, out of that n minus n 1, we choose n 2 of them and put them in the class C 2. That probability is p 2 to the power n 2. Like that, finally, we will have there are only n k many elements left. So, n k C n k, and that will give to the class k, that probability is p k to the power n k. So, this is the basic derivation of the multinomial distribution. If we simplify it, we will see that n factorial upon n 1 factorial into n minus n 1 factorial multiplied by, let us simplify this. So, that will give you n minus n 1 factorial upon n 2 factorial into n minus n 1 minus n 2 factorial. Like that we will go, and here we will get 1. multiplied by, as you can understand, p 1 to the power n 1, p 2 to the power n 2, p k to the power n k. And therefore, if we look at this cancels with this in a similar way corresponding to class 3, this is going to cancel with the numerator. So, finally, we will end up with n factorial upon n 1 factorial, n 2 factorial up to n k factorial into p 1 to the power n 1, p 2 to the power n 2, p k to the power n k. So, that is how the multinomial density function is obtained. I hope most of you are familiar with this, but still I wanted to clarify the density function. Now, we shall work with this formula. We write it slightly complicated way. So, we write it as e to the power minus n p 1 plus n p 2 plus n p k and divide by the same quantity. Similarly, again we multiply it by n to the power n and divide by the same quantity, and then this is the formula that we already had. Now, let us simplify this term. So, we can write this as e to the power minus n p 1, e to the power minus n p 2 up to e to the power minus n p k. Denominator we keep unchanged, and numerator again this one we write n to the power n 1 plus n 2 plus n k divided by this n to the power n, we write it as n p 1 plus n p 2 plus n p k whole to the power n multiplied by the standard density thing n factorial upon n 1 factorial etcetera, p 1 to the power n 1, p 2 to the power n 2 into p k to the power n k. So, this is little bit of algebraic jugglery that we have done, but for some purpose, as it will be clear in the next slide. So, we write the entire expression now as e to the power minus n p 1 into n p 1 to the power n 1 upon n 1 factorial. So, let us go back to the side e to the power minus n p 1 from here, then n to the power n 1 multiplied by p 1 to the power n 1, this we write it as n p 1 to the power n 1. Then there is a n 1 factorial which comes here, and therefore, entire expression as e to the power minus n p 1 to the power n 1 upon n 1 factorial into like that up to e to the power minus n p k to the power n k upon n k factorials. This whole thing divided by e to the power minus n p 1 plus n p 2 plus n p k multiplied by n p 1 plus n p 2 plus n p k whole to the power n. This is in the denominator divided by n factorial. This comes from here. Therefore, what we have done? So, we convert the whole thing into a Poisson type density function, and I am sure all of you are familiar with Poisson. A Poisson random variable x takes the value I with the probability e to the power minus lambda, lambda to the power I upon factorial I, where lambda is the parameter of the distribution. Now, recall that the mean and variance of a Poisson lambda distribution are both lambda. Now, the limiting distribution of a Poisson distribution or a Poisson random variable x with parameter theta, as theta goes to infinity, is a normal random variable with both the parameters equal to theta, that is normal theta theta. Therefore, limit theta going to infinity x minus theta upon root theta, this converges to normal 0 1, because we have standardized it by subtracting the mean and dividing it by the standard deviation, which is root over theta. Now, with respect to the above problem, that is the multinomial distribution, note that if n goes to infinity, then np j goes to infinity for all j is equal to 1 to k. Hence, if Pj is the probability of an observation falling into the class j, then the random variable xj denoting the number of observations of class j will have a expected value npj. This is very clear because the proportion coming from class j is pj for j is equal to 1 to k. With this now, let us examine the expression we have just obtained some time back. So, it is e to the power minus lambda power n1 upon factorial n1. So, this looks like a Poisson random variable with parameter np1 taking the value n1. Similarly, this is a Poisson random variable with np2 as the parameter, or we can write it at Poisson with np2 taking the value n2. Similarly, for the kth one, and in the denominator we have, it is a Poisson random variable with parameter np1 plus np2 plus npk. That means, it is a Poisson random variable with parameter n taking the value n. Therefore, the whole numerator is the product of k Poisson random variables x1, x2, xk taking values n1, n2, nk, and this can be treated as a product of k independent Poisson random variables with respective parameters np1, np2 up to npk. Now, as npj goes to infinity for all j, because if we take large samples, each xj can be approximated as normal with npj, npj. This we have just shown that as theta goes to infinity, Poisson converges to normal with theta, theta. Here theta is npj for the jth class. Now, since sum of independent Poisson distributions, what the ith one is Poisson with lambda I, is also a Poisson distribution with parameter sigma lambda I, that is the sum of individual parameters. The denominator of the earlier distribution is equal to sigma xj, that is Poisson with parameter n, as we have discussed just now. Therefore, the entire expression can be interpreted as probability xj is equal to nj for j is equal to 1 to k, subject to the condition that sigma xj is equal to n, because the sum of total observations has to be n, where xj is equal to Poisson with npj. That is, we are looking at the probability of the event x1 is equal to n1, x2 is equal to n2, xk is equal to nk, subject to the condition that sigma xj is equal to n. Since all the k values are not independent, there is a constraint there. Therefore, the degrees of freedom is reduced from k to k minus 1. Now, since n goes to infinity, each xj may be approximated as normal npj, npj, and therefore, once the observed value of xj is nj, we can write nj as distributed as normal npj, npj, subject to the condition at sigma nj is equal to n. Therefore, Nj is the observed value, Npj is the expected value divided by square root of Npj, that is going to give a normal 0 1 distribution, subject to the condition that sigma Nj minus Npj upon root over Npj multiplied by root over Npj is equal to 0. This is obvious, because if we cancel it, then this numerator will give me 0. Why it is happening? Because sigma Nj is equal to n, sigma Pj is equal to 1, and sigma Npj is equal to n is equal to Nj, where Nj is the observed value of the Xj. Now consider the statistic Nj minus Npj whole square divided by Npj. This may be approximated as the sum of square of k standard normal distribution subject to the linear constraint that Nj minus Npj upon root over Npj multiplied by root over Npj and summation over k is equal to 0. Hence, what is this? It is the sum of square of k standard normal variables with one constraint Therefore, this is a chi-square distribution with k minus 1 degrees of freedom, because we know that if there are m standard normal distribution x1, x2, xm, then x1 square plus x2 square plus xm square is chi-square with m degrees of freedom. So, this same thing typically we write it as sigma j is equal to 1 to k Oj minus Ej whole square upon Ej is distributed as chi-square with k minus 1, where Oj is the observed frequency of the class j, that is Nj, the number of observation coming from the class j, and Ej is the expected frequency of the class j, which we have just seen to be Npj. Therefore, observed minus expected whole square divided by expected, this sum for j is equal to 1 to k, that is the number of classes, is chi-square with k minus 1 degrees of freedom. So, let us go back to an example. Suppose a dice is thrown 600 times and the observed frequencies are like this: 1 appeared 95 times, 2 appeared 102 times, 3 appears 93 times, 4 appears 107 times, 5 115 times, 6 is 88 times. So, what we can see that there is some variation in the number of observations corresponding to the 6 different faces of the die, but does it mean that the die is not unbiased? We are not sure. We need to test that. So, what we are testing is H naught P1 is equal to P2 is equal to P3 is equal to P4 is equal to P5 is equal to P6, that is all the 6 probabilities are equal and each one of them is 1 by 6. So, this is the null hypothesis that we are testing against that die is not unbiased. So, what we do? We do the following: n is 600, there are 6 classes. Under the null hypothesis, Npj is equal to 100, that is expected number of observations coming from each class is 100, that is my Ej. Therefore, the statistic is going to be Oj minus Ej whole square upon Ej summation over j is equal to 1 to k, and we know that this is going to be chi-square with 5 degrees of freedom. Now, let us compute the value of the statistic. Therefore, it is 95 minus 100 whole square upon 100, 102 minus 100 whole square upon 100, 93 minus 100 square upon 100, 107 minus 100 square by 100, 115 minus 100 square by 100 plus 88 minus 100 whole square by 100. Now, you understand how to compute the statistic. So, this value is coming out to be 5 square plus 2 square plus 7 square plus 7 square plus 15 square plus 12 square, which is coming out to be 496 divided by 100, that is 4.96. Now, we shall reject the null hypothesis if this value is very large. Therefore, this is always going to be one-sided test. So, how it will work? So, here is a chi-square distribution. There are chi-square table available. I have given you one link for different degrees of freedom. Here I have just copied for 1, 2, 3, 4, 5, 6, and the cutoffs are given, which are the critical values for different alpha. We are looking at 5% level of significance. That means, we are looking at an alpha such that the probability the chi-square distribution is taking a value greater than this C alpha is alpha. So, these C alpha values are tabulated here. We have chi-square with 5 degrees of freedom. We are looking at alpha is equal to 0.05 and the C alpha value is given out to be 11.07. Therefore, what I am writing here is that the degrees of freedom is 5, alpha is equal to 0.05, the critical value is 11.07. The obtained value is 4.96. Therefore, we cannot reject at 5% level of significance. Therefore, we can accept the hypothesis at 5% level of significance. Let me now give you a practical example. Suppose a manufacturer produces an item and pack them in bags of 100. He claims that on the average in a bag 6% of the items will be defective. Now, to check the above claim, a customer opens a bag and tests all the items. He finds that 10 of the items out of 100 are defective. Question comes whether he should accept that on the average 6% of the items are going to be defective. That means that in another bag there may be lesser number of defectives. Like that, when we keep on taking different bags as samples, we may end up with at the end that on the average the number of defectives is going to be about 6% of the total number of products. Now, this is a very typical problem on decision making, where the producer and the customer have opposite interests. A producer wants the hypothesis will be accepted, so that the customer will go for placing purchase orders, because if the purchaser is convinced that the number of defectives is small, then he is likely to go for purchasing the items from the producer. However, the customer or the purchaser will be careful that he does not buy defective products. So, will not be willing to accept the consignments with proportion of defectives at a higher level. Therefore, if the test fails that the number of defectives on the average is greater than 6%, then customer may not like to purchase these items from this producer. So, typically how the test will be carried out, that is decided in advance before the actual examination of the item starts. So, we are not going into the detail of the statistical procedures. So, let us look at how we test for H naught p is equal to 0.06 versus H 1 p not equal to 0.06. So, we are looking at two-sided tests. Therefore, it is a two-class problems where C1 is the class of defectives and C2 is the class of non-defectives. Therefore, under H naught, probability of class 1 is equal to 0.06 and probability of class 2 is equal to 0.94. Therefore, the test statistic Q is chi-square with 1 degrees of freedom. Why 1 degree? Because there are two classes and we know that if there are k classes, then the chi-square will have k minus 1 degrees of freedom. The obtained value of the Q statistic is therefore 10 minus 6 whole square divided by 6 plus 90 minus 94 whole square divided by 94, which is coming out to be 2.84. Therefore, now the problem is whether we should accept the null hypothesis or reject. For that we have to refer to the chi-square table and we see the following, that for 1 degrees of freedom at 5% level of significance, the critical value is 3.84. We have taken the table from this link, so that you can also check how to see a chi-square table. But going back to the problem, we can see that our obtained value is somewhat smaller than the tabulated value of C alpha when alpha is equal to 0.05. Therefore, we cannot reject the null hypothesis at 5% level of significance. Now, let us consider a small variation of the problem. Suppose we want to ask what is the maximum number of defectives in the bag for the customer to accept the null hypothesis. That means that if the number of defectives is less than that value, say k, then the customer is going to accept the null hypothesis, otherwise he is going to reject the null hypothesis. So, what is going to be the maximum number of defectives? That is going to be the question. So, we are therefore looking at the minimum value of k such that k minus 6 whole square divided by 6 plus 100 minus k minus 94 whole square divided by 94, that has to be greater than equal to 3.84 if we have to reject the null hypothesis. That is, k minus 6 whole square multiplied by 1 by 6 plus 1 by 94 has to be greater than equal to 3.84. Now, that boils down to k minus 6 whole square multiplied by 0.177 has to be greater than equal to 3.84. That is, k minus 6 whole square greater than equal to 3.84 divided by 0.177, which is coming out to be 21.69. Therefore, we shall reject the null hypothesis if k is such that k minus 6 whole square is greater than 21.69. Therefore, we can easily see that the value of k can be 11. Hence, we can see that the maximum allowable number of defective is 10, because in that case k minus 6 whole square is coming out to be 4 square, that is 16, which is less than 21.69, and we are going to accept the null hypothesis. But if k is equal to 11, then this is coming out to be 25, and therefore, we are going to reject the null hypothesis. Therefore, the maximum allowable number of defective is 10. Now, let us consider another variation. Suppose the number of defectives in the bag is found to be only 1. Question is, what will the customer do? Note that since the number of observed defective is 1, the obtained value of q is going to be 1 minus 6 whole square by 6, then 99 minus 94 whole square divided by 94, this is coming out to be 99, because since there is only one defective, 99 of the other elements or items are non-defective. This value is coming out to be 4.425, which is greater than the C alpha, that is 3.84, which we have seen some time back. What does it mean? Does it mean that the customer will not purchase the bag because we are rejecting the null hypothesis? No, the customer will go for purchasing the bag because number of defective has been found to be very small. Then what does it mean? That we are going to reject the null hypothesis? It means that we are rejecting that p is equal to 0.06, that is the proportion of defectives is not accepted, because the test suggests that the proportion of defective is quite different from 6%. Now, we can use chi-square test in a slightly different way as follows. What I am saying, chi-square test for hypothetical population which is completely specified. So, these are hypotheses more fundamental in nature, because a natural question is that if the population is completely specified, mostly say normal population, then we can go for parametric inference. So, what does it mean? I stated at the very beginning that parametric inference is more robust or powerful than non-parametric. But parametric inference works under normality assumption. So, if we are given a sample and we can test that it is actually coming from a normal population, then we are really happy, because we can use all our parametric inference techniques. So, that is why sometimes we try to check if the given sample is coming from a standard distribution, and that is why I am saying that the hypothesis that it is coming from a normal population itself can be questioned, and we need to make sure that is correct, that is that assumption is correct, and therefore, we like to verify that on the basis of a sample observation. So, how to do that? Suppose the population is completely specified and there is no unknown parameter. We know that if there is no unknown parameter, then the density is completely known to us, and therefore, the distribution is known to us. But based on that knowledge, what we do? We try to partition the entire sample space into k mutually disjoint classes. So, let according to the underlying assumption, that is H naught is the proportion of population that falls under the jth class. Then the number of observations falling in the jth class is expected to be n p j 0, because this is the population proportion, n is the sample, therefore, expected number of sample in the jth class is n p j 0, but actual number of observations in the jth class may be somewhat different, as we have already seen. Thus, there may be a gap between the actual observations from the jth class, which if we call n j, between n j and n p j 0. The sum of the square of the deviation normalized by the expected value gives the desired chi-square statistic. This we have already explained. So, to consider a sample of size 1000, that is drawn from a probability distribution, we claim that the sample is coming from normal 0 1 population, but we need to verify it. Therefore, before proceeding any further, we want to check the validity of the above assumption regarding the population distribution. So, how to do that? That is the question. So, we proceed as follows. What we are doing? We decide to partition the data into 7 classes. Then, from the normal table, we get the cumulative distribution of the classes. Suppose we partition it as follows: minus infinity to minus 2.5, minus 2.5 to minus 1.5, minus 1.5 to minus 0.5, minus 0.5 to plus 0.5, similarly plus 0.5 to 1.5, 1.5 to 2.5 and 2.5 to infinity. Thus, there are 7 classes. So, these are the 7 classes. X is less than minus 2.5, x is between minus 2.5 to minus 1.5 up to x is greater than plus 2.5. Now, the question is, what is the expected class probability p j 0? So, x less than minus 2.5 is 0.0062. How to get that? We get it from the normal table. So, this is minus 2.5, this is 0. So, this is the cumulative probability of a standard normal distribution taking value less than minus 2.5, that is 0.0062. Therefore, that we have obtained. Now, let me do it one or two more for your understanding. What is the probability that a standard normal random variable is between minus 2.5 and minus 1.5? So, again we go back, less than minus 1.5 is 0.0668, 0.0668 and less than minus 2.5 is 0.0062. Therefore, we get the difference is 6060. So, the probability is 0.0606 and that is what we have written here. In a similar way, we can compute for all. I have given the entire normal table for your help. You can compute from here the class probabilities for all the 7 classes, which I am showing here like this in this column. Suppose the actual observations belonging to these 7 classes are as follows: 10, 80, 220, 400, 195, 60 and 35. Therefore, expected class frequency, how do we get? We multiply these values by 1000, therefore, we get 6.2, 60.6 to 41.7 like that up to 6.2 and that should sum up to 1000. So, this is the expected class frequency, this is the observed values. Therefore, we need to compute the square of their difference, which is coming out to be like this: 14.44, 376.36 up to 829.44. Therefore, for each one of them we calculate this normalized thing by dividing by E j, and these are the values that we obtained, and the sum of these values sigma O j minus E j whole square upon E j, summing over j is equal to 1 to 7, we get 154.05. Is it too high? We do not know, but looking at it, I can itself see that this cannot be from normal 0 1, because x greater than 2.5, that number should be very small, but here we find that number is pretty large, which is 35. And if we look at this sum of square, we can see that that is giving us a huge value, making the sum to be too high. but still it can be from normal 0 1. So, let us check with the chi-square value. So, again we look at the chi-square table. This is going to be chi-square with 6 degrees of freedom, because there are 7 classes, and therefore, k is equal to 7, and therefore, k minus 1 is equal to 6 is the degrees of freedom. Therefore, we look at chi-square with 6, and for 0.05 the critical value is 12.592. Therefore, so first we look at what is the critical value at 1% level of confidence, that is 16.812, and at 5% level of confidence it is 12.592. Therefore, since for degrees of freedom at 6, at 1% level the value is 16.812. Therefore, we reject the null hypothesis at 1% level of significance. Therefore, quite naturally it has to be rejected at 5% level of significance as well. Or in other words, we are not going to accept that this data is coming from a standard normal distribution. However, one can think of that if n is the sample observations and they are coming from a continuous random variable, one can expect that the final decision may differ with the different values of k, and the boundary is chosen to demarcate the class. I have just given you an example with only one way of choosing the class boundaries, and the number of classes is equal to 7. One can think of making different class boundaries, different number of classes, and test. I leave it as an exercise for you to check with a few different classes and computing the corresponding chi-square statistic. Therefore, one important problem is that here we have considered elements belonging to a particular class. Therefore, the points are losing their individuality. Can we make a test where we will look at all data points into consideration to test such a hypothesis? In case of continuous distribution, comparisons can be made between observed and expected cumulative relative frequencies for each of the observed values. So, instead of putting them into several classes, we look at each point in an sorted order, in an increasing order, and check up to that point what is the observed frequency and what could have been the actual frequency if we are looking at certain underlying distribution, and then we will try to see how much difference it is actually generating. So, let us go and illustrate. So, several goodness of fit test statistics are functions of the deviations between the observed cumulative distribution and the corresponding cumulative probabilities expected under H naught. So, we shall study one major algorithm in this regard, which is called Kolmogorov-Smirnov one sample test. The test goes as follows. We design an empirical distribution function f n based on the n samples taken from the population. So, we have the ordered, as I have said, that we have to take them in sorted order. So, x 1 less than x 2 less than x n is the ordered sample. What does it mean? Below this point there was no observation, that is f n x is equal to 0 if x is less than x 1, and x n has to be 1 if x is greater than x n. So, for any x more than this, we know that the entire sample is less than that. Therefore, the cumulative empirical distribution function f n will take the value 1. In between, for x I and x I plus 1, if these are the observed statistic, any x between this interval means that there are I many observations out of n less than this. Therefore, what we are getting the cumulative probability to be I by n. So, that is how we design the empirical distribution function f n, where x I is the ith order statistic, f n x is the proportion of sample values less than equal to x, n f n x is the number of sample values less than equal to x, possible values for n f x n are 0, 1, 2 up to n. As you can understand that if I multiply this by n, we get that the number of sample values less than equal to x. What is the distribution of n f n x? The distribution of n f n is binomial with n theta, where theta is equal to f x. What is f x? F x is the distribution under null hypothesis. That is, the CDF is equal to f x. Therefore, under the null hypothesis, the distribution function f x means that probability and observed value is less than equal to x is f x. Therefore, we are considering it to be a binomial distribution with f x is the probability of falling in this side and 1 minus f x is the probability that it will fall on the other side of x. Therefore, probability n f n x is equal to k is equal to, out of n we are choosing k, that is n c k, they are getting the probability f x to the power k because they are less than equal to x, 1 minus f x to the power n minus k because they are falling here, where k is equal to 0, 1, 2 up to n. Therefore, probability f n x is equal to k by n, I am just dividing both sides by n, is equal to n c k f x to the power k 1 minus f x to the power n minus k. So, if that is a binomial distribution, then expected value of n f n x is equal to n theta is equal to n f x, where f x is the distribution we are comparing with, and its variance is going to be n f x into 1 minus f x. This is coming from binomial distribution. What does it imply? It implies that expected value of f n x is equal to f x and variance of f n x is equal to f x into 1 minus f x by n. In one sample Kolmogorov-Smirnov test, we check if the unknown population distribution f x is actually a known distribution f 0 x, that is, we are checking f x is equal to f 0 x versus f x not equal to f 0 x. This test statistic for this purpose is the maximum pointwise deviation between f n x and f 0 x for all x belonging to R. Therefore, the test statistic is going to be d n is equal to maximum of f n x minus f 0 x for x between minus infinity to infinity. This statistic is then compared with critical values of tabulated for different values of n from the Kolmogorov-Smirnov one sample statistic table as the one given in the following link. So, I am giving you here a link to check Kolmogorov-Smirnov cutoff values or critical values for one sample test. So, let me illustrate it with an example. Suppose we have taken 10 observations from uniform 0 1 distribution. Let these values be like this 0.8, 0.16, 0.21 up to 0.85. Therefore, what is f 0 x? F 0 x is uniform 0 1. Therefore, f 0 x is equal to x for x belonging to 0 1, because uniform 0 1 distribution, that means it is ranging only from 0 to 1, that means it takes values only from 0 to 1. What is f 0 x? Is equal to 0 for x less than equal to 0 and f 0 x is equal to 1 for x greater than equal to 1. Therefore, f 0 x will have a following shape. It is 0 up to 0 and then it goes uniformly like this at 1 1 and then it takes the, it becomes horizontal. So, that is how this uniform distribution will look like. Hence, we compute the sample cumulative frequency at each point x and compare that value with the f 0 x and we consider the supremum of the differences, and that is what is going to give me the Kolmogorov-Smirnov statistic. So, what we are doing? We had these values. So, x less than 0.08, we did not get any observation, so therefore, that is 0. For between 0.8 to less than 0.16, we have got only one observation 0.08, therefore, f n x is equal to 0.1, 0.16 to just less than 0.21, we have got two observations 0.8 and 0.16, therefore, f n x is equal to 0.2. Similarly, for up to 0.85, we got 9 observations and at 10th observation in the ordered sample is 0.85. Therefore, for x greater than equal to 0.85, we get the value 1. Now, what is the value of the supremum? To do that, let us first look at a graph. So, this is the graph that we have drawn for our understanding. So, this red line is the f 0 x, that is the CDF of uniform 0 1. The blue line, it is the sample f n x. So, what is happening? Till 0.8 it is 0, at 0.8 we get one observation, therefore, it goes up to 0.1, then the next observation is at 0.16, therefore, it gets a jump up to 0.2 and like that the last one is at 0.85 and that gives a jump up to this point, that is 1. Therefore, for each of these interval, we can always look at what is the maximum of the difference for any x belonging to that interval. Say for example, in this interval the maximum difference coming out between the red line and the blue line is this much, that is the supremum. Therefore, we have computed those values when f n x is 0 and x is less than 0.8, then the supremum is coming out to be 0.08 because f 0 x at 0.08 is equal to the same value, f 0 x is equal to x. Similarly, for 0.08 to 0.16, f n x is 0.1, therefore, the supremum is coming out to be the difference between 0.1 and 0.16, that is 0.06. 0.16 to 0.21, the f n x is 0.2, therefore, the maximum difference is coming out is from 0.16 and 0.2, that is 0.04. 0.21 to 0.29, the value is 0.3, therefore, the supremum of the difference is coming out to be 0.21, 0.3 minus 0.21, that is 0.09. Like that, we have computed all of them and we have got the maximum value to be 0.22. Now, if we look at the graph, we will find that the maximum value is coming here. So, this is the maximum difference which is coming out to be 0.22. So, the statistic for us is going to be that 0.22. Therefore, we need to compare this value with the critical value that we can take from the Kolmogorov-Smirnov table. So, let us look at the table. We have value of n is equal to 10, at 5% level of significance it is 0.409, we are looking at only 3 decimal spaces. At 0.1 we are getting 0.369. So, we are comparing our obtained value with these values. What we have obtained is 0.22. Therefore, we accept the H naught at 5% level of significance, and also we cannot reject it at 10% level of significance. That means, we are going to accept it also at 10% level of significance. Now, a natural extension of the above test is to check if we take two different samples x1, x2, xm and y1, y2, yn, are they coming from the same distribution? In that case, what is going to happen? We are not going to compare the sample frequency distribution with a standard hypothetical distribution, rather we shall look at their sample cumulative functions for both x and y, and we will check how much they differ. So, if the maximum value is greater than some threshold, then we are going to reject that they are coming from the same distribution, otherwise we are going to accept that. So, that we will consider in lecture 8, but before that, in the next lecture we shall see some other two sample tests. In particular, our focus is going to be on randomness testing, that is whether the sample taken by us is actually random. Okay friends, I stop here today. In the next class, we shall do these problems. Till then, thank you.